Alright, this video is looking at how to calculate circuit diagrams. So far we've been dealing with series circuit, parallel circuit, and the introduction to complex circuits in the lab. And from that you have gathered some data and you've looked at the properties of both series and parallel circuits. Series circuit, if we can just quickly review that, in a series circuit, which is drawn down the bottom here, when current travels through a series circuit, it only has one pathway. And because it has only one pathway, the total resistance of that given circuit dictates the current, or the amount of current that can flow through there. So it doesn't matter if I measure current at this point, down the bottom, or just going back into the battery. Current is always going to stay the same in a given series circuit at a given resistance. So we summarize that by saying I0 is equal to I1, which is equal to I2, which is equal to I3, which just means that in a series section or a series circuit, current remains the same throughout. The second thing is voltage. And when you measure the voltage across the battery, if it was, for example, 6 volts, that means there's 6 joules of potential energy for every amp as it moves around the circuit. That means that across each resistor, voltage is dropped, or voltage is used, or energy is used, and that energy cannot be any more than the energy that's supplied by the battery. So if each of these resistors was the same resistance, so 2, 2, and 2, for example, then the voltage drop across each one of those, if this was a 6-volt battery, would be 2 volts, 2 volts, and 2 volts. And they always have to add up to 6 volts. And that is the case for any circuit. Doesn't matter if we're dealing with a parallel circuit or a series circuit or a complex circuit. The voltage that travels around the entire circuit, whatever that voltage rating of the battery is, that's how much energy is dropped over the entire circuit. So in a series circuit, we would say that the voltage is the sum, so V1, V2, V3, of all the voltage drops across each load. In a series circuit, resistance adds up. Because there is only one pathway, that means that the more objects that you put in the way, or more loads you put in the way, the greater the resistance. And there is no other pathway to go around it, so the more barricades you put in, the greater difficulty it is to move through the circuit. So resistance is the sum of all the different resistors or resistances in that circuit. In a parallel circuit, it behaves a little bit different, because in a parallel circuit, what happens is you are creating multiple pathways for the current to travel. So I want you to think of it as a road. It's like going down a single lane road and then suddenly moving to 2 lanes and then moving to 3 lanes and to 4 lanes. If you think of the amount of cars that can travel across any given point in a 4-lane highway versus a 1-lane highway, it's going to be 4 times as many. And in a circuit, when you do that, you are adding what we refer to as lanes or pathways, or what I'm going to refer to as branches. So when we go through the example question, I'm going to label, say this first one, B1, and I'm going to call it branch 1. This one's going to be branch 2, and this one's going to be branch 3. So as we add more branches or more lanes, more current needs to be supplied throughout the circuit. And the reason more current has to be supplied throughout the circuit is because every time you go from one side of the circuit to the other, the same amount of voltage is dropped. So if this was a, say, 6-volt battery, then you're going to have 6 volts drop from this side to this side of this resistor. You're going to have 6 volts on this branch, and you're going to have 6 volts along this branch. Well, because every branch needs the same amount of voltage, you really need more. You can think of it as delivery trucks, and think of the current as the delivery truck. So if I only have one resistor, I only need one delivery truck or 1 amp of current. If I have a second resistor in parallel, I need to bring in another truck to get that energy there. If I add another branch, I'm going to have to add another truck. So again, think of the trucks as the current. And I need to supply more current or more method for the energy to flow around as I add branches. And that's why this really here we can think of as branch 1 plus branch 2 plus branch 3. So we're going to add up the current. So the current is the sum of all the branches. The voltage is the same across each one of those branches, but remember that as the voltage drops, you're delivering the same amount of energy to each one of those branches. In order to deliver that energy, we need to supply more current. So they're directly related. Now, since the resistance is an inverse relationship, as you add more branches, the resistance goes down. Unlike a series circuit where you add more resistors in series, the resistance goes up. When you add more resistances in parallel, or when you add them in branches, it's an inverse relationship. So we have a 1 over, which indicates that really resistance is decreasing as we add more branches. Now we're going to go through an example question to help you start thinking about how to calculate these circuits. So I want you to think about the circuit that we're going to look at. So we're going to start off, we always start from the positive side, and we're going to move through the circuit. And again, I want you to think of resistor 1 here, and think about the total current. All the current that comes from the battery must go through resistor 1. Just like you did for your complex circuit lab, all that current needs to go through resistor 1. And then once it gets to this point, then it's going to divide off into 3 branches. And again, I'm going to call this branch 1, branch 2, and branch 3. So we're going to have X amount of current coming through resistor 1. It's then going to go down branch 1, branch 2, branch 3. All those branches, if I added up the current, are going to add up to my total current. So I'm going to have I0 really equals the I of branch 1 plus the I of branch 2 plus the I of branch 3. The reason that we have to keep adding those is because when we go from one side of a branch all the way to the other side, in this case it's going to be 6 volts. So 6 volts are going down branch 1, 6 volts are going down branch 2, 6 volts are going down branch 3. So in order to supply those 6 volts, or whatever voltage is left over, as you will see in our calculations, you need to increase the current that's coming out. So we're going to keep referring back to this diagram, and we're going to go through a series of steps in how to calculate certain aspects of the variables here. So the first step in any circuit calculation is finding the total resistance. Doesn't matter if it's a simple series circuit, whether it's a straightforward parallel circuit, or in this case a complex circuit, you need to find the total resistance. And in order to find that total resistance, you need to, that allows you to calculate the total current. Alright, so let's go through this step. So this first step here is looking at all the individual branches. So let's go back to that previous diagram. So let's erase all this so we can kind of break it down into what we are looking at. So again, we're looking at resistance. We're finding total resistance. So in order to do that, I have to figure out what is in series with each other. So if I take a look at resistor 1, resistor 1 is in series with this whole parallel section. So when we go back to the equation, you're going to see R1 plus 1 over branch 1 and so on. And that's because R1 is in series with the resistance of this parallel section. Because if I go from this point all the way around, I'm going to drop off 6 volts. And because I'm dropping off 6 volts, some of it's going to be dropped off at R1, the rest of it's going to be dropped off in the parallel branch. So that's what's happening in this section here. So this is that first resistor we're going through. This is calculating the resistance of that parallel section. I have further broken it down into the actual resistors. So again, we have R1 we're starting with. And then if you think about branch number 1 has 2 resistors on it. Those 2 resistors are in series, so because they are in series, we use the series circuit rules, and that means that we're going to take R2 plus R3. So we're going to find the sum of that. Branch 2 only has 1 resistor, so we're just going to use the 1 resistor rating. And branch 3 has, again, 2 resistors, so we have to find the sum of those resistors because they are also in series with each other on that specific branch. So using the numbers that correspond to the diagram, again, resistor 1 has a resistance rating of 10. We now have 22 and 10 that are in series, so we're going to add that up. 100 is just 1 resistor, so that's the given resistance of that branch. And then the resistance of branch number 3 is the 39 plus the 22. Now, to calculate this and to calculate any complex circuit, to simplify, you want to break it down into the equation I have written here, and you want to learn how to use your calculator to plug in this information. So you want to type in 10, and then you're going to add, and then you're going to put a bracket, and then you're going to do the fractions. So you're going to have 1 over 32 plus 1 over 100 plus 1 over 61 end bracket, and then find the negative 1 on your calculator. And what this negative 1 does is when you press your equal sign, it's going to change all these fractions into a decimal, add them together, divide it into 1, which is the reciprocal, and then add it to the 10. And that's going to give you your total resistance of that circuit. And I would suggest practicing that. You can stop the video right now, type into your calculator that information, make sure you understand how to use your calculator to your advantage, that you can do this in one step to get this unrounded number, because that will save you a lot of time in these calculations and save you a lot of headaches by not writing down every single digit for every single fraction and so on. So you definitely want to practice that, and if you're not sure how to do it, again, when I'm back in the class, I can help you through looking at your calculator. The number that you get here is going to be your 27. That's going to be 27.34 blah blah blah. Again, that is ohms, right? That's your resistance level of the entire branch. For the purposes of these calculations, we're always going to round things to 3 decimal places. I know it doesn't follow the significant digit rules, but this is just a consistent way So you always get the same answers that I will be posting. And again, this number here and any if you're going to use this number in another calculation, you want to use this entire number, the unrounded number. If I'm asking for a final answer, then you're just going to round it to 3 decimal places. Once you find that total resistance, then that allows you to calculate everything else in the circuit. Gives you a foundation to do that. Your next thing, or next step you should be doing, is then finding your total current. And again, when you write it out, when you communicate it, to find your total current, you're going to use your total voltage over your total resistance. So again, we know total voltage is 6. We know the resistance now is that 27.34 blah blah blah. And now we are going to come up with that unrounded number. And then now this here, that 0.219 amps is the current that travels through the entire first section of that circuit. So this is what would be actually going through resistor 1. So again, we found that I0 is going to be 0.219 amps. That means that as the current comes out, if I was going to measure it here, that would be my total current. That would also be the same number. That's the same number. Going through resistor number 1, it's also 0.19 because there's no other branch, there's no other route for it to go. So all of it has to go through that resistor. Then once it passes here, then it's going to break up. That 0.19 is going to break up into the 3 branches. So step 2 is you want to find the voltage drop over the series section of the circuit. And that's because if we look at the diagram, so we have 6 volts here. Remember that 6 volts is being dropped across the entire circuit. So when it moves through that first resistor, some of that 6 volts is going to be used up to push that current through that first resistor. So what we do is we're going to take that resistor, or in some cases resistors, that are in series and figure out how much energy is being used before we get into that parallel section. So we're going to calculate using Ohm's law. V1. Now we know that the current running through V1 is that total current that we just talked about. We know the resistance rating of that is 10. So now we can calculate the voltage. So we know that the voltage drop across resistance number 1, or resistor number 1, is at 2.194 volts. And that's how much energy is required to push that current through that particular resistor. Now, because that 2.194 has already been used, then we don't have all that 6 volts anymore. So now, once we know how much has been used over that series section, now we know how much is going to be going across that parallel section. So we're going to use our 6 volts, which is our total voltage. Then we're going to really subtract the voltage across V1, which we just calculated. And we're going to come up with that 3.806 volts. Now, the rule for a parallel section is that each branch will have the same amount of voltage. This is the voltage that is remaining from that 6, because 2.194 was used up already on that first resistor. So this 3.806, that is going to be across each of these branches. So that's going to be 3.8, that's going to be 3.8, and that's going to be 3.8. And that is the rule for a parallel section of a series circuit. But in order to find that voltage, we needed to find out how much was lost or how much was used in that first resistor. And that's why we did this section here. Now another question that they could ask you is figuring out, in this case, V2. So how much voltage is dropped across a specific resistor on branch number 1? So remember, this is going to be B1. And so in order to do that, we need to figure out how much current is running along that branch. And then we can use Ohm's law to figure out how much voltage is being dropped over resistor 2. So we know we can calculate the current of B1. So we know that the voltage of B1 is 3.860 and so on voltages, because that's what we calculated already. That's what's remaining from that 6 volts, and we know that that's going to be the same voltage across each of these branches. We're now going to be able to divide by 32, which is your total resistance of that branch of B1, which is 32. And so we're going to be able to divide those two, again using Ohm's law, and that's going to get us our 0.119 amps. Because this is in series, this whole branch here, that means 0.119 amps is the same all the way down that specific branch. So now again we can use Ohm's law. We can go V2 equals I2 times R2. Again, we know the current, and now we're going to use the specific resistor, so this is R2. So we don't use the total resistance of that branch anymore. Now we're just looking at the specific resistor, and then that's going to get us the voltage drop across each of that particular resistor, at that V2. Now, we know that the voltage across this branch here, from here to here, is approximately 3.8 volts. We know that we calculated 2.6 volts across this resistor. To find R3, we can take the 3.8 and then subtract the 2.6. Now these are just approximate numbers. We'd have to use the decimal places properly and so on, but because you know the total voltage drop across branch number 1 and you know the voltage of one resistor already, you can find the difference between the two to find that third one. So you don't always have to use Ohm's law. If you understand the idea of a series circuit and a parallel circuit, you can use those rules to your advantage and be able to calculate other unknowns in a much simpler way. Now we can use branch number 2 as another example. So we could figure out the current that runs through branch 2. We know that the V4 is going to be that 3.8. We've already figured that one out in the previous question, because we know that each one of these branches is 3.8 volts across. Since there's only one resistor there, then it's going to take all the voltage, which is going to be the 3.8. We can, though, use that information of 3.8 plus the resistance of that branch to figure out the actual current running through there. So in that case, we're going to use the voltage of V2, which is that 3.8 plus all its decimals. We can divide it by the resistance, which is the 100, and then that's going to give us our current that runs down I4, which is really branch 2. So we now know the current of branch 1, and we know the current of branch 2. We haven't calculated branch 3 yet, but you can use the rules. We know that all of these currents of each branch is going to add up to the total current. So we can take the currents of B1 and B2 and then subtract it from the total to give us our B3. And again, that's just using the advantage of understanding what the parallel circuit rules are and knowing that I0 equals I1 plus I2 plus I3. And when you apply those rules, again, you can avoid doing some calculations by understanding that you can take the sum of those to find our third branch when we know the other two branches. The last page here is just looking at all the answers for every single resistor. What I think you need to do is go back, and it's really important to map out the circuit, look through the solutions that I've shown you on the video so far, so you have a good understanding of where those numbers are and how they apply to the rules of a series and a parallel circuit. The rules that are applied are referred to, when you go through your textbook, are called Kirchhoff's laws. And you'll have Kirchhoff's laws for a series circuit, which is what I went over at the beginning of the video, and then you'll also have the Kirchhoff's laws of the parallel circuit, which was also outlined at that beginning of the video. So it's really important now to go back, review what I've discussed in the video, take a look at the diagram, slowly go through it, and look at the calculations as well as how do the rules that I went over at the beginning apply. And try to figure out your other resistors. And then when I come back, we'll be able to go through this again in more detail, and we can start answering questions about different components of the circuit.